Well, thank you, Professor Luo, for the introduction. Can you all hear me?
Yeah. Sounding clear.
Yes. Great. So, and I'm sharing my screen as well. You can see my screen, right? All right. So, with that being said, this topic today and it's my favorite topic I would like to talk about is invariant signatures for AEC objects. This was basically a theory that we developed a couple of years ago. And over the years, we have successfully tested in many different scenarios for supporting the BIM interoperability. And for the problem that we are looking at, we probably we are all familiar with the concept of building information modeling, or have heard about it, use it at certain point in our work. The idea of BIM is that it was by design comprehensive. It's supposed to support the collaborations between many different stakeholders, and therefore the interoperability of the building information modeling is key to the success. But however, in the reality, there is really a lack of interoperability when it comes to the transfer of models between the software provided by different software providers, which can cost our society billions of dollars easily, because there will need to be a lot of manual efforts that go into fixing the model, or finding missing information, or even creating the model from scratch, right? So this is a big problem. And one important observation of the problem is that it will be very difficult or even impossible if we rely on the industry itself to solve it. Just like the problem of the interoperability between the Mac computer and a Windows system, right? So there is a tendency, just by nature, they don't want to be compatible with each other. So to push that forward, the industry formed an alliance, which later became what's called the Building Smart. And Building Smart has published the industry foundation classes as the standards, right, to help with the BIM interoperability, which is great, which is considered to be the most promising solution by most of our community members. However, because of the BIM standards, it also allows flexibility. And the reason is because it is designed to be comprehensive. So it builds in flexibility. For example, for the IFC standard, you can use IFC's property single value to represent any properties. And you can use IFC building element proxy to represent an object that was not explicitly represented otherwise. So the issue of interoperability still exists, even if everybody is using industry foundation classes or follow that standard. So the idea is that using IFC, we can try to facilitate a paradigm shift from what's called many-to-many interoperability to a many-to-one, so that everyone can export into IFC and import IFC. But like I said, even if that's the case, you can still not guarantee the fully seamless interoperability. And if we look at the future of our AEC industry, there are many technologies that are going to make our industry much more intelligent and autonomous, right? Such as the robotics, sensing, the AI, which is a huge trend right now. And in my vision, all of this needs to be organized by the building information modeling, because this is the essential model. Just like in the Professor Gong's presentation earlier, you have seen a lot of very significant simulations. But when it comes to the infrastructure side and the building side, right, all the information is still supposed to come from the building information modeling. So with that being said, let's take a look at some, example IFC data, right? For those of us who are not familiar with IFC data, it's pretty much just a list of entities which each line represents an entity, and each entity will has attributes. And then if we look at the representation of the geometry, which is supposed to be the most mature part of the building information model, the figure 1 here shows a representation of a line segment, basically, right? And we all know that 2 points define a line. So this is straightforward. So if you look at the IFC shape representation, it is calling the 8430, which is the IFC polyline, which is defined by 2 points, right? 8428 and 8429. So then you have the coordinates of these 2 points, and this one is even simpler. It's in 2-dimensional. So it's very easy to understand. But when it comes to the 3D representations, it can be a little more complex, right? So the figure 2 shows a representation using what's called a clipping operation. And this is, you basically take 2 3D shapes and, use binary operations such as union or difference between them. So in this case, we have what's called an IFC Boolean clipping result. And it is using 2 solids, right? So one of the solid is called a IFC extruded air solid. So this is a very classic representation of a 3D shape in the IFC paradigm, and in fact, in general, in 3D graphics representation in general, it's called sweeping solid. So the idea is that basically you get a 2D shape, and then you extrude that 2D shape through another direction, usually like the normal direction, or a direction that is not in the same plane, and then you get a 3D representation, right? So the other 3D shape here is what's called a polygonal bounded half space. Now it's becoming a little more interesting here, because it's a, as the name suggests, it's a half space, right? Just imagine, so it's indefinite, okay? So half space. And how the half space is being defined, again, it's, oops, wrong direction. So here's a figure to help us understand. So basically, you take a plane and you cut the whole universe, the whole space in half, right? You get 2 halves of that space. And then you have a polygon that help you define the boundary of the 3D shape that you want to define, and an origin that help you place that half space into the coordinates. Okay, so in this case, it is using this IFC plane to represent the cutting plane to cut the whole universe in 2, and then it is using this what's called IFC axis to placement 3D. Again, this is a very classic representation of the placement and orientation in the IFC paradigm. And then the IFC polyline is used to define the boundary of the polygon. But then there's a 4th parameter, which is a binary parameter, true or false. And according to the Building Smart definition, this is called an agreement flag. And they explained it as, if the agreement flag is true, then the subset of the half space, again, you're cutting the whole space into 2 halves, right? And then you need to select one of them to use in your representation. So if this flag is true, then the subset is the one that the normal points away from. And if the agreement flag is false, then the subset is the one the normal points into, okay? So in this case, it is true, right? So if it's true, it means you are picking the one that the normal points away from, okay? So now think about it. Can you tell me which of these 2 half spaces are we picking? Just think about a few seconds. Okay, so I hope the answer that you get is not clear, right? So this is a problem, because the true meaning of the agreement flag, although they have clearly explained it in the specifications, but it can still be having ambiguity and clarity, right? So, for example, normally the true is used to prefer to the positive case, right? So, such as the direction the normal points into. But the potential ambiguity of the away from caused by the unbounded nature of a half space, because both the positive case and the negative case seem reasonable to say it is the one that the normal points away from. Considering that in the positive case that the half space can be regarded as the departure of the normal, and without testing, such doubts will never get clear. Okay, so another example that we want to use is in the visualization of building information models, right? So this is one model that we downloaded from the National Building Information Model Society or committee. It's an open access model, so everyone can download it for free. But when we open this duplex apartment model in different BIM software, you can see even the visualization of them can be quite different, right? Sometimes even the transparency of components may not show up as correct. So this was surprising because the geometric part was supposed to be the most stable part of building information modeling, but still there is a big problem when it comes to the interoperability. So what we developed a few years ago, we took the FC data and the schema that was defined by the Building Smart and certain level of due diligence, we can produce a systematic understanding of the entities in the FC, which is the foundation for us to actually enable the full interoperability, even if we are using FC models, right? And there are also side benefits. We can produce BIM utilities and tools. In other words, the BIM software can be produced based on this method. We call it a DSD approach because it takes the data, the schema, and the due diligence. So following this method, I took an initial try and find some very simplistic bridge models with piers and the deck, and try to, make sense out of the FC entities that are representing the geometry and, so on and so forth, right? So we start with this cone frustum shape of the bridge pier, and it was using the boundary representation, which is another type of classic 3D representation in the FC paradigm. So based on our understanding, we try to implement a visualization algorithm that can help us visualize it. So you can see this is a comparison of a visualization of that cone frustum bridge pier with a commercial tool with the Solibri model checker. This was our algorithm in Java language. The results pretty good, right? But not yet. When it comes to putting different objects together, for example, we realized, okay, the placement was not correct. And that was because we didn't implement the FC axis to placement 3D at that point. So then, this type of error caused us to look back at the data and further refine the algorithm. So the figure 8 here shows, one example pathway of how the different FC entities can be used, in this case, to represent the 3D shape using the BREP boundary representations. I'm not going into detail, but essentially you can break down the 3D shape first to the surfaces, and then surfaces can be broken down to lines. Lines can be broken down to points. So with that being said, we just refined the algorithm based on better understanding. Eventually, we were able to visualize this simple bridge correctly. And at the same time, we generate the systematic understanding of the geometric entities from the FC data. And we also tested on this duplex apartment building. So as you can see, the visualization results was pretty good, and it was comparable to the commercial tools at that time. So with that being said, now I would like to introduce the concept of invariant signatures. The idea is that instead of solely relying on the standard such as FC standard, we also need to look at the inherent features of an object, an AEC object in this case. And the three types of features that we focus on include the geometry, of course, geometric features, and then the location, the relative location. Again, think about the placement of the object in the space, right? And then the third part is the mechanical and the material properties. So this is how we define the invariant signatures. We published in 2021 formally, but the idea has been conceived much earlier than that. We define as a set of intrinsic properties of the object that distinguish from others and that do not change with data schema, software implementation, modeling decisions, and or even language cultural context. So that means you can apply it everywhere, right? And it also should uniquely describe the object and provide all the information needed for various analysis. Okay, so now just to show an example to help us understand the geometric features that compose the geometric signature, let's look at this cone-frustum shape again. And how do we define cone-frustum shape? We can define using these three rules, right? Like the first one, there needs to be the top and bottom faces need to be circles, and the top and the bottom faces needs to be in the parallel. And then the axis that is connecting the top and bottom faces should be in perpendicular to the faces. Okay. So from the mathematical definition, all the points on the boundary of a circle have the same distance from the center of the circle, right? So that's by definition. So this definition was used to identify a circle. And to find the center of the circle, we use this equation 1 here, where x, y, z are the coordinates of the center. Xi, yi, and zi are the coordinates of the different points on the circle. And interestingly, in the practical representation in computer graphics in general, we don't really render the real circle because you will have indefinite amount of points, right? So usually what we render is approximation, and a lot of time we see a hexadecagon. It means you have 16 points used to represent a circle as an approximation. So in this case, then we can check the distance between each of the 16 points and the center point, right? So theoretically, this distance should be exactly the same. But due to the rounding errors in the practice, again, strict equation for the criteria would have failed because you are never going to get exactly the same distance, right? And a tolerance of error is needed. So to analyze this needed tolerance, again, we go back to the data, right? So the distance from each of the 16 vertices or the 16 points to the center for both the bottom and the top surfaces can be computed using the equation 2. Okay, and then this figure shows the results of those distances. In this case, we have 16 of them. And we ignore the units of measurement because they don't really matter in this context. Based on observing the computed distances and the maximum rounding error, we set a tolerance of error to be 6 points after the decimal points. And then this was checked through comparing the mathematical representation of the two faces using the equation 3 and the criterion 1. So in equation 3, the x, y, z are the coordinates of any points of the shape, and a, b, c, d are obviously the 4 parameters used to define a plane. And then to decide the parameters for a hexadecagon, again, a polygon with 16, remember, points, right, or size. 3 points were randomly chosen from its 16 points, and then these parameters A, B, C were solved by plugging in the coordinates of the 3 selected points. Plugging in the solved A, B, C, then you can solve the parameter D. So you can solve the whole equation here. All right, so now the rule guarantees that you have a cone-frustum shape is not to you don't want to exclude cone-frustum, right? So that is where this axis perpendicular to the bottom top faces come into play. And also the cylinder is a special case of cone-frustum because when you have the size of the 2 circles that are the same, then you have a cylinder, right? And then this can be further distinguished by criteria number 2. So if the top and bottom faces have the same size, then the shape is a cylinder. Right. So with that being said, we developed the algorithm based on this invariant geometric signature, and then we successfully tested on 3 more bridge pairs retrieved from online places, online sources. And then an error tolerance in the equidistance check was decided by taking the maximum rounding error observed. Although it was tested to be successful in this data, but it may not be the case in all the possible testing data, because the sounding error, the rounding error depends on the software used, or the modeler or the configurations chosen by the modeler. In the ultimate classification algorithm that includes sub-algorithms for all the known categories, a good combination of this error, a good combination or estimation of this error tolerance may be obtained by analyzing a large amount of training data. So also the use of the relative value to represent error tolerance, in this case a percentage or a dimension of the shape, may be more robust than the use of absolute value to represent this rounding error. So remember, we use the 6 points after the decimal points, right? But this may also be dependent on the range of the absolute sizes of the dimensions. For example, when you compare 2 data values that are close to 0, then their relative difference can be large, where the absolute error can be small. So the same rationale it also applies in comparing, the absolute value with the relative value. It also applies to relations used in the patterns of our sub-algorithms. Specifically, the relative relations are expected to be more robust than the absolute relations. For example, the parallel relation between the top and the bottom faces of this frustum shape is more robust than the absolute relation. Let's say if we assume both of the 2 faces are horizontal, right? But if certain assumptions are known to be valid, let's say the structure is standing vertically, then the absolute relations may be preferred because they're simpler to use. For example, if the assumption that all piers stand vertically, just like this one, then it's easier to say that the 2 faces need to be horizontal. Okay. All right, so this table here summarizes the geometric signatures of AC objects in a rectangular parallelepiped shape. So we have used 9 categories of geometric features, including the number of subcomponents, the number of faces, cross-sectional profile, extrusion direction, dimensional ratios, number of straight lines and curves and boundary line connection angles, lengths, and the 10 directions. And then the locational information is reflected by the XYZ coordinates. When you place the object, remember we have the axis to placement 3D, right? So then this table shows the signatures for a cylinder shape, and then we have also example signature for ring shape, for eye shape, so on and so forth. Because the eye shape is pretty common in the steel beams and columns, and the ring shape is common to use for pipes and things like that. And after the geometric signatures were developed, we extracted features of 1,252 object instances from our collected data. In addition to showing example use of the data side, we developed a rule-based algorithm to do object classification, which we tested on 389 object instances from our architectural model. And then the algorithm used all the parameter values from the 14 features and successfully classified 336 object instances into the correct categories of beam, column, footing, slab, and wall. And then the collected and processed data we deposit into the Purdue University Research Repository, which is publicly available. You can download it from there. Okay, so this is an example algorithm that we have developed for representing for the object classification into different categories, such as I-beam, C-beam, column, footing, wall, etc. We also develop algorithms that can classify the detailed types of beams, such as U-beam, C-beam, I-beam, L-beam, etc. These are examples that shows the features from the geometry that we use as part of the classification algorithms. remember one of the feature that we use is the turn direction, right? So which means when you walk through the contour line of this shape, at a certain point you need to turn, right? Let's say for this I shape, for example, when we walk through this point to this point to this point to this point, we turn right twice, right? But if we look at this shape, we start from this point, and here we turn right, but here we turn left. So that's an example of how or why we need to use this feature to distinguish certain scenarios. Because if we don't have this feature, these two shapes will be identified as the same by the classification algorithm, right? So that feature is needed, in other words. We also developed an algorithm that can automatically classify or identify class structure. So this is the algorithm on the right-hand side. So we collected 1,891 objects in total, and then we used 1,325 for training and 566 for testing. These are the results. It shows in the categories of beam, slab, column, footing, and wall. In certain cases, 100% precision recovery achieved, right? But in certain cases, such as in the footing case here, the performance was very low. So then we did error analysis. We look into, okay, why these were the cases. So the shapes of 167 footings or foundations, right, more precisely, in the experiment were similar to the columns because they are both cylinder shape. And therefore, there was misclassifications. So which tells us the geometric signature itself, it may not be sufficient. So then we add the locational signature. Remember, the second category of the features was the locational information. So we add the locational signature, and that solves that problem perfectly. So then we take the invariant signatures and start applying it to different scenarios. So the first scenarios we look at is the transfer of model between architectural design and structural analysis, right? So in this case, we have two categories, geometric features and material features. And we just put the locational features here inside the geometric features. And then for the material properties, we have these very classic ones like mass density, Poisson ratio, shear modulus, etc. And we devised the 5-step method for applying our invariant signatures to solving any practical BIM interoperability problem. So in this case, we're solving the interoperability between architectural design and structural analysis. So essentially, we need to collect data and then pre-process them and then develop invariant signature algorithm iteratively, and then you evaluate the algorithm, right? So for this scenario, we developed these were synthesized models. So as you can see, we have 1 bay or 2 bay with or without slab or walls that we created to help us devise our algorithm. And then we created slightly more complex structures for testing our algorithm to see if they can stand the test, right? So this is what the results look like. So basically, for those of you who are not familiar with structural analysis, there are many different software that you can use. We pick STAAD. It's one of the structural software, and we selected it because it can take text data as input, right? So we can manipulate it or play with it. So in this case, we created a gold standard for our data, and then as you can see, it's the one on the left-hand side, right? So in order to analyze the structure, you need to define the structural model. So this is what the structural model definition looks like in STAAD. And the one on the right-hand side is the one that was automatically generated by our invariant signature-based algorithm. So as you can see, it's pretty comparable, right, to the gold standard. And then we further tested on a real project. So this is a 2-story building with staircase and everything. So these are the results. As you can see, the results it was pretty good. In overall, it has 98% precision, 94.9% recall. But again, it was not perfect, so we looked into the errors. So, for example, there were some incorrectly generated slabs because our algorithm, it depends on the training data that we use, and the training data, it did not have such cases where you have an opening and a staircase, right? So it didn't catch that. But once we know this was the case, we can further integrate this case into the algorithm to solve it. This is another example. When you have a slab that extends beyond the boundary of the building, the algorithm make a mistake, which is okay. So now we realize it, and again, we put it back into the algorithm. So with that being said, we want to just summarize here. We have developed this invariant signature theory with initial geometric and material signatures that can be used to capture the essence of architecture, engineering, construction objects. We can use them in various engineering and management analysis and model exchange tasks. So this theory goes beyond the state-of-the-art of AC information representation based on data schema and enables robust AC information representation that can be ignorant or regardless of software implementation, modeling decisions, and or language cultural context. So we advance the empirical knowledge also in the area of BIM interoperability by offering a new data-driven method to use invariant signatures for solving the practical problems in the BIM applications, so that we can support the many-to-one paradigm of the BIM interoperability and brings the seamless universal BIM interoperability one step closer to reality. The theoretical and empirical knowledge in the area of BIM interoperability can support an improved model exchange between the different AEC processes. So in fact, we started with this architectural and structural scenario, but we already have done a lot of scenarios, such as between architectural design and quantity takeoff as part of construction management task, from architectural design to building energy modeling, building energy simulation, from the architectural design to building code compliance checking, between architectural design and the constructability analysis, such as modular construction or construction with robotics and automation, so on and so forth. We also tested, we also further expand this concept to the infrastructure domain, and we have tested between the drainage model design, which is an important part of the infrastructure, right, of modern societies, between the drainage design and the quality assurance of a drainage, and also between the pavement design of roadways and the quality assurance of that as well, in collaboration with the local state department of transportation here. So with that being said, just because of time, I want to stop there. Again, this is just a tip of the iceberg. If you're interested, we have a website. You can click on that, and it lists all the information, all the resources related to invariant signatures. These are the references that are relevant, and acknowledgements. We would like to acknowledge the support of the National Science Foundation. Cannot do the work without their support, but these opinions, findings, conclusions are those of the authors. Okay. Thank you all.